Hello, and welcome to our latest edition of nanoCHAT PuBCLuB, which is the Ionic Viper YouTube series that helps members of our community talk about the recent publications that they've had. I'm Shirley Lynn from the Naval Academy, and I'll let today's guest introduce herself.
I'm Nancy Williams from the Keck Science Department of Claremont McKenna, Pincer, and Scripps Colleges. Yeah. That's what you need to know about me.
Thanks, Nancy. So today we're going to be talking about Nancy's recently published article in Organometallics entitled Geometric Control of Carbon-Carbon Reductive Elimination from a Platinum-4 Pincer Complex. And as usual, a link to this publication will be found in the description that accompanies this video. So we always like to start off by asking our guests what the motivations and context was for doing this particular study. And I just wanted to note that this paper is related to your JAX 2007 communication, for which there is a literature discussion LO on Viper and is part of our Pride collection.
And we could probably also put a link in the notes to both of those things as well. So another thing I want to point out about this paper is that it is going to appear in a special issue in honor of MS Brookhart's 80th birthday. He goes by Brooke, for those who didn't have the pleasure of knowing him when he was traveling the conference circuit. And I was a postdoc with Brooke, so it's a great honor to be able to publish in that particular issue. The motivation behind all of this was actually to do something completely different, as is often the case in research. But what we have said the motivation is for doing all of this research was that when we started the work that appeared in the 2007 communication, there was a widely believed conventional wisdom that reductive elimination between sp and sp carbons was always much, much faster than reductive elimination with sp2 carbons, which was always much, much faster than reductive elimination with sp3 carbons. So in that paper, I'm going to go ahead and do something dangerous, which is to try to share my screen here. This is the 2007 communication. Is that coming through okay?
Can see it, yep. Okay,
great. So I want to draw your attention to this bottom reaction here, going from 1 to 4, in which methyl triflate, which is effectively just a methyl plus reagent, is added to this platinum pincer ligand, which is the terdentate ligand that's got a phenyl ring in the middle and nitrogens on the ends, with a methyl group. So that's going to put 2 methyl groups on the platinum, one in an apical position and one in an equatorial position or a basal position. And so that methyl group can either reductively eliminate with the CH3 group, or it can reductively eliminate with the CH2 group. And if it reductively eliminates with the CH2 group, you should expect to get that agostic complex that we get on the right. And if it reductively eliminates with the methyl group, the CH3 group, we should get methane. And that is exactly what we see, is we see a mixture of the two. And so why that was surprising was the conventional wisdom was you should only see 4, you should not see any 3, but we definitely did. So that's what that paper was all about. And in this paper, let me close something that keeps popping up because it's slightly annoying. There we go. And in this paper, we actually did this work not long after the JAX paper, but like many things at small undergraduate colleges, it ended up getting shoved to the side while we worked on a lot of other things. And so this special issue was a perfect opportunity to pull together the co-authors and to make this thing happen. So in this study, we were really interested in creating 2 isomeric complexes, which I am now going to attempt to bring up on a share screen. Is that coming through all right?
Yes, success.
Excellent. Okay. So the goal was to prepare the square planar complexes similar to one in the top left, where you have an NCN platinum methyl, and then you put a phenyl plus on top. And another complex that we have on the top right, where you have an NCN platinum phenyl, and then you stick a methyl plus on top. And both of those are isomers of one another. And one thing that we know about 5-coordinate complexes is that they isomerize very, very quickly with one another. And so we expected those to just interchange, to scramble. And so we then have an opportunity for a lot of different carbon-carbon couplings because each of those platinum isomers has 3 carbons on it. But what we saw, in fact, was that instead of getting 3 possible combinations from each one, we actually only saw 1 product from each isomer, and they do not rapidly convert. So that's what we were looking at in this paper.
Wow. So in terms of those of us who aren't, necessarily into organometallic chemistry as much, it sounds like you found a really fundamental sort of reactivity that you can now speak to. Are there other metals that exhibit similar behavior? Is this the only example?
It's the only example we've found where reductive elimination seems to be much faster than 5-coordinate isomerization. The only case that we found where it's competitive is the 2007 JAX paper, where there seems to be some scrambling competitive with the reductive elimination. But this is the only case we found where it's faster. The fact that the reductive elimination chemistry seems only very slightly influenced by hybridization continues to kind of upend that conventional wisdom. One other thing that we found in this paper that does seem to have a really controlling effect is something first spotted by Alan Goldman about a decade ago, which is that for a phenyl ring, I'm going to stop sharing here so that you can see my hand motions. For 2 methyl groups to reductively eliminate, they just have to come together, and because they are more or less spherically symmetric, or they're cones, orientation doesn't matter much. But a phenyl ring can either be oriented that way or anywhere in between. And it turns out for a methyl group to couple with a phenyl group, they have to be in this kind of an orientation rather than this kind of an orientation. If it's side on or edge on like that, the ortho protons get in the way of the reductive elimination, and you don't have the available orbital for coupling that you would have with an edge on or a face on phenyl ring. And in this complex, when the phenyl ring is in the plane of the molecule, it really can't rotate easily because the arms of the nitrogen ligand prevent that rotation. Let me go ahead and pull up another scheme from the paper that kind of shows all of these possible interactions.
So one thing I really appreciated about the paper was the incorporation and use, I see you're going to talk about that next, of computational work. I thought this was a great example of the partnership between experimental work and computational work.
So gratifyingly, 2 of the co-authors on this paper are former students of mine who are now professors in their own right, which was another motivation to finally get this paper out because they'd like to get tenure. Allegra Lieberman Martin, who is at Chapman University, and Mary Van Vliet, who is at Spelman College. And Mary Van Vliet is a computational chemist. And she was a joint student with myself and Bob Cave, rest in peace. He was a professor at Harvey Mudd, and we lost Bob this last year. He was an undergraduate professor of mine back in years that began with a 1. And so it was really nice to be able to publish one last paper with Bob, and also to be able to publish a paper with Allegra and Mary. So Mary did all of this computational work. She did it back when she was an undergraduate, and then now in the year 2022, she updated all of the calculations with higher level theory than we were able to do a decade ago. And what this shows is all of the barriers that you can imagine for this complex that seem sort of reasonable. They're all in kilocalories per mole. The complex on the left, this 3' is the one in which we start with a phenyl ring in the plane and we put a methyl plus on top. And this 4' in crimson is one in which we show the methyl group in the plane and the phenyl group on top. And gratifyingly, what we see is that the lowest energy barrier from the blue 3' is this 3.7 kcal barrier to making the sp2 coupling between the apical methyl group and the face-on phenyl ring. Whereas the phenyl ring in the plane is edge-on, and so it can't reductively eliminate. Whereas for 4', the lowest barrier, although it's actually close to one of the other barriers, to a product we don't see, The lowest barrier is one that gives the methyl phenyl coupling with the face-on phenyl ring to give toluene. And all of these reactions are irreversible, so it's completely under kinetic control. Surprisingly, we don't see any of the coupling to 7'. Probably there's some error in our estimates of those activation barriers. At a lower level of theory, interestingly, that barrier is higher. And so we would predict that it's less competitive, but these are the numbers we got. And so we're not going to go to a lower level of theory just because it matches our experiment better. This is what we found.
So really, really exciting work. Where are you going to go from here with this particular project?
We're not. This is really the end of the line for this project. Oh, one other thing I should say from this figure before I drift onto that. The isomerization between 3' and 4', between the blue and the red manifold, actually only has a barrier of 17.4 kilocalories per mole, which for those of you who don't stare at activation barriers all day is a rate constant of about 1 second to the -1. So it's incredibly fast. The reason we don't see that isomerization is just that the other reactions are faster. So this is not an unusual case where that isomerization isn't quick. It's incredibly speedy. It's just the other reactions are faster in this particular case. So yeah, this is really the end of the line for this chemistry. We could extend it by doing some methyl ethyl propyl butyl phenyl chemistry, by just continuing to change those R groups and seeing what compounds reductively eliminate. But we really felt like we had mined this for the chemistry that was likely to have an important impact on people's thinking. And so we've really moved on to some other things. We have some other ligands that we are working with now that are really well designed to promote CH activation trans to that ligand. And so we're trying to do some basic alkane activation, trying to do oxidative addition of some CH bonds. And our computational studies suggest that this is going to work much better for iridium than for our platinum systems. So I'm going to have to learn some new things and become an iridium chemist. So that's on the to-do list for my upcoming sabbatical this next academic year.
Well, I would certainly say alkane, activation and reactions is definitely up Brooks' alley, and he would be delighted, I'm sure, with any results that come from that study. It's also really refreshing to hear someone at a faculty member at PUI say that they finished something. So congratulations.
Right.
Well,
the original plan was that this was going to be finished in about 2010. So it's not like I finished it on time. But we did bring a project, a system to what we feel like is its logical endpoint.
Well, congratulations again. And I just wanted to say thank you to Nancy for recording this nanoCHAT with me, and to everyone who's watching this video on YouTube. So please feel free, if you're a member of the Ionic Viper community, to comment and ask Nancy questions on our Discord channel, specifically the ComChat channel. And then please feel free to join us for our next episode. Let us know also if you'd like to be a future guest on nanoCHAT PuBCLuB. Thanks, everyone.
And I would be remiss if I did not point out that Shirley Lynn also has a paper in this special issue that's going to be coming out in honor of Brooks' 80th birthday. Well,
we'll see if we can get a PuBCLuB recording there. Thank you.
That would be fantastic.
Bye, everyone.